So in this lecture, we discuss the converse of Cauchy theorem, which is called Morera theorems. So what is the Cauchy theorem? If a function is analytic within and on a closed simple contour, then integration around that contour is equal to 0. Now in the converse part, what we discuss, if a function, so the statement of this theorem is, if a function f of z is continuous function in domain D. So it is a continuous function in domain D, and for every closed contour C in D, integration of fz into dz around C is equal to 0. In that case, then function f of z is analytic. This function is analytic within a domain D. So within a domain D. So this is a statement of a converse of Cauchy theorems. So in this case, there are two conditions. Condition number 1, this function f of z is a continuous function. And condition number 2, for every closed contour, even we can say that simple closed contour, integration is equal to 0. In that case, when the two conditions are satisfied, in that case the function is analytic within a domain D. So in the condition of in the Cauchy theorem, if function is analytic, then this condition is true. But here there are two conditions. One is the function is continuous, and second is integration is equal to 0. Now to prove this result, first, now what is the proof of this result? Now suppose this is a some domain D at which the function is continuous, and in this is some z naught which is a fixed point in this domain. So this is a fixed point, and this is a z which is a variable. So this is a variable. Z naught is a fixed point and z is a variable. Now the value of integral, we already know that the value of integral from z naught to f of s ds, from z naught to z, which is independent of path. So which is independent of path, it means it only depends upon z and z naught. Since z naught is a fixed point, so it only depends upon a z naught. So but depend upon the variable upon z. So it only is depend upon the z which is a variable because z0 is a fixed point. So what do you mean by it is a independent of path? It means if we take the integration from z0 to z along any curve from this to this, from this to this, and from this to this, so they have the same values. If they have the same value, so it is independent from path. So it depends only at the extreme point, which is z0 and which is a z. Since in this case z0 is fixed point, so it only depend upon the variable z. So remember that the value of this integration is independent of path, but it means it depend upon the z only. Now I consider a integration fz which is equal to this integration. So which is equal to z0 to z, this integration, and here f of s into ds this value. So this is treated as equation number 1. So I take this integration which is indefinite integral of f of s, f of z, and this f of z is continuous as that is given in the point. And this z0 plus h, the z plus h, this is some another point. So this is a, so here it is a correct this, it is a z, not z0. So correct this. So this is a z. At this z plus h be a neighborhood of a, be a neighborhood of a point z. So z plus h is a neighborhood of a point z. So in this formula, we can define the value of f of z plus h. So that is f of z plus h, which is equal to integration z0 fixed point. Here it is z plus h, and here it is f of s into ds. So this is the equation number 2. Now subtract equation number 1 from equation number 2. So what we get? We get f of z plus h minus f of z. This value is equal to z0 to z plus h, which is f of s into ds minus z0 to z into f of s into ds. If we multiply by minus sign, then this can be written as plus. This is from z0 and this is a z. So in this case, this is the integration from z to z0. Now this integration is from z to z0 plus z0 to z plus 1. So this value will become integration of f of s into ds, and this is from z to z plus h. So we get this value. Now if we divide this value by h, then this value is by h and this value is by h. So we get this value by h. So what we get? We get this integration. This value is equal to 1 by h integration from z to z plus h of f of s into ds. So which is equation number 2. So from this we get this values. Now this value f of z plus h, h is some point positive number. So this integration, this values, this can be written as f of z plus h minus f of z over f of z plus h minus and over h minus I take here f of z and this values. Now this value is equal to, what is this? So this is the integration, this values, and this is a 1 by h into integration, which is from z to z plus h into f of s into ds. Similarly, this value can be written as 1 by h integration f of z, this value, and into ds, and this is from z to z plus h. When we simplify, so this is a constant taken outside, this will become a z plus h minus z, that is a h, so that h is cancelled with this term, so we get this values fz. Now this is again by taking the next step, this can be written as this value 1 by h, so this is a integration of 1 by h, and this is from z to z plus h, so this can be written as f of bracket f of s minus f of z into ds, this values, and this is absolute values. Now again by using the next step, so this is less than equal to 1 by absolute value of h. Since h is positive, so it will become a h. And next is integration, which is from z, and this is from z plus h, and this value is f of s minus f of z into dz, this values. Now we get this values, so this is written as equation number 4, either 3 or 4, so you can take it as either 3 and 4. Now in the given theorem, the function is given as continuous function. So here we are using the definition of continuity. Now since function f of z is continuous, which is a continuous function. If it is a continuous function, then for epsilon greater than 0, epsilon is some positive number, there exists a delta, greater than 0, such that f of s minus f of z, this value is less than epsilon for every modulus of s minus z is less than delta. Now this point is in the neighborhood of z. So it means what is h? H is less than epsilon. So this can be written as by using this concept. This is a continuity. This is a concept of continuity. By using this concept, this value is less than 1 by h, this values, and this is less than epsilon. Then taking the integration, this will again get the h, so this will become a epsilon. This will become a epsilon. Now from this, what we get? From this we get f of z plus h minus f of z over h minus f of z, which is less than epsilon. If less than epsilon, epsilon is greater than approaches to 0. So as z h approaches to 0, so as epsilon approaches to 0, so as epsilon approaches to 0 and it implies h approaches to 0, so it implies limit h approaches 0 f of z plus h minus f of z over h, so this is equal to f of z. So this may be written as derivative of f dash z, which is equal to f of z. So from this we get the derivative of f dash z, which is equal to f of z. So here I can write it as f dash z, which is equal to f of z. Now since derivative of this function exists, then it means this function f of z is analytic function. Analytic function. This is analytic function because it is differentiable everywhere. Since it is differentiable everywhere, so this function is analytic function. Now, as we discuss in the higher order of derivative in Cauchy integral formula, if function is analytic, then its derivative is also analytic. So it implies f dash z is again analytic function. If this is analytic function, so what is this? This value is equal to f of z. So it implies f of z is a analytic function, is analytic function, analytic function in domain D, function in domain D. So which prove the converse of Cauchy theorems. So sometime it is asked as the converse of Cauchy theorem, sometime it is asked as the Morera theorems. So now after that, the next is very important, which is called a Cauchy inequality. Cauchy inequality. So this is again very important theorem. So first understand the statement. The statement is if a function f of z, this is analytic within, which is analytic within and on a circle. So within and on a circle C. So what is circle C? Which is whose center is z0 and whose radius is r. So this is a circle C. This function is analytic in these values. And in addition to that, if function f of z is bounded, it means f of z less than equal to m. This is bounded. M is some positive number for every z on C. So then in that case, then nth integration of function at point z0, the absolute value of nth derivative of z0 function at point z0, which is a less than equal to m into n factorial over r raised to power n. So this is a statement of the Cauchy inequality, right? Now we will prove the result. So solution, we can also say that proof, you can use any terminology. Now from this, if I take a given C circle, so what is the given part if I take, so this is a circle, this values. Now this point is center, which is Z naught, and this is taken as the radius R. So this is a C. So this is a circle C. Now what is the given part? Given part is Z minus Z naught is equal to R. So modulus is equal to R. So it means this can be written as R into e raised to power iota theta. So R is radius. So it means d of z, which is equal to R e raised to power iota theta into iota into d theta. So I take it as equation number 1. Now to my result. Now we know that from Cauchy integral formula of nth order, the nth derivative of function over z naught, what is its value? So this is equal to n factorial over 2 pi iota, and this is integration around c. So here I write it as f of z into dz over z minus z naught raised to power n plus 1. So this is a Cauchy integral formula. So here I write it as in this way. Now taking absolute value on both sides. So it implies, so just use mathematical notation. So which is equal to absolute value of fn z naught. So this is equal to absolute value of n factorial 2 pi iota around c, which is fz over z minus z naught raised to power n plus 1 into dz. So it is nothing, it is a fz. So just so remove this, link this shape. So I just first remove this. Now when this is in absolute value, so this is less than equal to its absolute value. Its absolute value means n factorial over 2 pi. So remember that, because the modulus of iota is equal to 1 and this value is equal to modulus of fz, and this value is equal to z minus z naught raised to power n plus 1, and this value is equal to modulus of dz. So this is a around integration c. Now in the given part, this modulus is less than m. So this value will become n factorial m over 2 pi, number 1. Then integration 0 to 2 pi, because this integration will converted into theta. So this value, this is less than m, I write here. So this is 1 by r raised to power n plus 1. Now taking the modulus of this values, if I am taking the modulus of this value, so this is basically modulus of r iota e raised to power iota theta into d theta. So remember that modulus of iota and e raised to power iota theta is 1. So we will remove that. R is positive and d theta is positive. So here we write it as r into d theta. So just I in the simplified form. So in the simplified form, the value is r into d theta. So what we get? We get this is r into d theta. This values. So this value is equal to, now from this value is equal to n factorial m over 2 pi 0 to 2 pi into 1 by r raised to power n into d theta. So this will converted as n factorial m over r raised to power n. So this is our result, and this is called a Cauchy inequality. So this is very important result. Now after that, the next inequality, the next theorem is called a Lovely theorems. So the statement of this theorem is, so first write it as this, and this is this theorem. Now what is the statement of this theorem? The statement is, if a function f of z is entire and bounded, entire mean analytic, entire and bounded, bounded mean bounded, entire and bounded, then f of z is constant, then f of z is constant. So this is our statement of this theorem. If the function is entire and bounded, in that case the function is constant. This is very important result. Now solution, yeah, we can say that proof of this theorem. Entire mean it is analytic. So remember that if function is entire, then it means function f of z which is analytic in the entire domain, entire domain. So this is a function which is analytic in the entire domain. Now if we take arbitrary point, let z be a some arbitrary point, arbitrary point in domain, arbitrary point in the given domain, then by Cauchy inequality, then by Cauchy inequality, the nth derivative of function at point z which is less than equal to m into n factorial over r raised to power n. So it is a by Cauchy inequalities. Now since the function is bounded by m, because function is also given that bounded by n, now for n equal to 1 means first derivative. So this inequality will become, so its derivative at this point less than equal to m by r raised to power n. So this is m by r, because n is equal to 1. So this is m by r. Now the given domain is entire domain. So in that case r approaches to infinity. So since it is, we are taking our question in a circle of a radius r, but we want to prove for the entire domain. So in the entire domain r approaches to infinity. So in that case, let r approaches to infinity. If r approaches to infinity, then this m by r f dash z less than equal to m by r, which approaches to 0. So it implies f dash z is equal to 0. So it implies this function f of z, which is equal to constant. So which is our result? If function fz is entire and bounded, then it is called a constant. Now this theorem is very important. This is very important. So we discuss one of the example. For example, I take this function fz, sine of z. Now this is a function when z belongs to complex number. As we know that when when this is a real number, when this function is a real number, so this function is bounded. So sine of z is bounded in a real domain, but it is not bounded in the complex domain. So remember that sine z cos z is bounded in the real domain, but it is not bounded in the complex domain. So how we will prove it? Suppose this function on complex domain fz, which is equal to sine of z, is bounded. Suppose this is a bounded. As we know that it is an entire function, it is analytic because its derivative is exist. So it is an analytic function. Also f of z, which is a entire functions. So which is a entire function. Now it is entire as well as bounded. Then by the previous theorem, which is called this lovely theorem, this theorem, entire and bounded are constant. So it implies f of z, which is constant, which is impossible, which is not true because sin z is not a constant function. Hence, our supposition is wrong. If our supposition is wrong, then this function is not bounded. Then it implies sine of z is unbounded. So it is a unbounded in a complex domain. So remember that. So what we get from the previous result, previous theorem, a non-constant, a non-constant. So what we get? A non-constant entire function is unbounded. Non-constant entire function is unbounded. So remember this result. This will be helpful in UGC exam. A non-constant entire function is a unbounded. So similarly, we can take some another example, fz, which is equal to cos z. So this is a non-constant and entire function, so it will be unbounded. Similarly, you can take many other examples. So it prove our the lovely theorems. After that, we will discuss a very important theorem which are series theorem. So that is called a Taylor theorem as well as Laurent expansion या Laurent theorem. So that we will discuss in the next lecture.